This is the video to watch before worksheet 8. It will cover Mazur chapter 8 force. This is going to be really long, so I suspect it might wind up being split into two parts. I don't know yet as of the time I'm recording this. And I think I originally intended for you to read the book first. That may not be necessary, but if you do have time, you might consider looking over Mazur chapter 8. As usual, if you look at the marked up copy, it really tries to box in red the things to pay attention to. And this set of slides is phys8 slides 08.pdf in the files area. So one really super duper important thing about forces is forces always come in pairs. So when object A and object B interact, the force exerted by A on B is minus the force exerted by B on A. In other words, the force exerted by B on A has the same magnitude but the opposite direction from the force exerted by A on B. So if you push on me, it's really a force between you and me. So if you push on me, part of that very same force is my pushing on you. It's not that they're two separate forces, it's really just two ways of looking at the same force. So if I'm pushing on you, then as a part of my pushing on you, you are pushing on me. And that is Newton's third law, and it is widely misunderstood, and it is the reason why so much time in the earlier chapters of Mazur's book were spent on momentum and on isolated systems and on two objects interacting only with one another, and on the, for example, the acceleration of the two objects that interact only with one another being, their ratio being minus the reciprocal of the ratio of the masses, as you saw in chapter 7. So these are called interaction pairs, okay? So the force exerted by A on B and the force exerted by B on A are an interaction pair. They have equal magnitude. They have opposite direction. This is always true. If you're if you really want an example where it contradicts this, there is sort of an example in magnetic forces, but even there's kind of a third party involved, which is the electromagnetic field. So in our course, it's always true. So this is called Newton's third law, and it's a difficult idea. So it's important when you're enumerating forces always to keep track of what object a force acts on. And when you want to determine the acceleration of object A, for example, that is given by the vector sum of all the forces acting on object A and then divided by the mass of A. So that's Newton's law number 2. So the first thing we wrote down here was Newton's law number 3, which is the force exerted by A on B is just the vector negative of the force exerted by B on A. Mazur's book doesn't write on. It says A comma B or B comma A. The trouble is that different textbooks have different conventions on which one goes first, so I will always try my best to write on so that you don't have to worry about remembering which convention our particular book uses. So if you want to figure out how object A accelerates, so little a is acceleration and big A is saying we're talking about object A, how confusing is that? It is the reciprocal of the mass of object A times the sum, we have this big capital sigma for the sum, of all of the forces exerted on object A. So you have to be able to enumerate all forces acting on object A to figure out what object A is going to do. You do not have to know the forces exerted by object A to know what A is going to do, but you do have to know the forces exerted on object A. So it's very important to keep straight these two halves, these two sides of the same coin here. So this half is relevant for determining what's happening to object B. This half of this side of the coin is relevant for deciding what's happening to object A. And there are almost no circumstances where you would use these two sides of the coin together they would usually appear in different diagrams. Okay, so we did Newton's third law, which tells you that there are two sides. If a force is a coin, then that coin has two sides. And one side of that coin, if the coin represents the interaction between object A and object B as a force, then that coin has one side, which is the force exerted by A on B. And that same coin has another side, which is the force exerted by B on A. And they're the same magnitude, but they point in opposite directions, and they affect different objects. One side affects A, one side affects B. I mean, it's almost like saying there are two sides to each financial transaction. And that is actually not such a crazy thing to say, because in a sense, a force is like a little microscopic momentum transaction once you apply it for some specified interval of time. But I'm digressing. I shouldn't digress. So that was law number 3. This is law number 2, which tells you how to figure out how object A accelerates if you know object A's mass, and if you know all the forces acting on object A. Now there's also Newton's first law, which says in an inertial frame of reference, object A moves at a constant velocity or stays at rest if and only if the vector sum of forces acting on A equals 0. Now you might say, well, that's kind of redundant with the second law, because the second law would say, you see, if this vector sum of forces equals 0, then the acceleration of A equals 0. So the second law already tells you that if the vector sum of forces acting on A is 0, then the acceleration of A will be 0. And if the acceleration of object A is 0, then clearly either it's at rest and staying at rest, or it's moving at constant velocity. So the modern point of view is that law number 1, when expressed in this way, is basically redundant. So what law number 1 instead is kind of philosophically taken to mean is that this second law only makes sense in an inertial reference frame. Right, in an inertial frame of reference. So in fact, this Newton's first law, which is the third thing that we wrote down, in the modern picture is actually taken to be a definition of an inertial frame of reference. And if you don't work in an inertial frame of reference, then Newton's second law is not strictly true. To make Newton's second law work in non-inertial frames of reference, you have to add additional terms which we call pseudo-forces or fictitious forces. That's beyond the scope of Physics 8, although I've always thought it would be fun to add it to Physics 8 or 9 in some form. So bear in mind that if you want Newton's laws to work as advertised, you should work from the perspective of an inertial frame of reference. You push with a steady force of 25 newtons on a 50 kilogram desk fitted with ultra-low friction casters on its 4 legs. Why ultra-low friction? So that you can assume the only horizontal force is the force of your push. There's no other pertinent horizontal force. How long does it take you, starting from rest, to get the desk across a room which is 25 meters wide? Well, let's start by drawing an x-axis. Let's say the x-axis points to the right, and then let's say the push exerted by me on the desk. I'm going to say D for desk, okay? D equals desk. So I'm going to say it has an x component, which is plus 25 newtons, okay? So I'm saying it's pointing in the x direction. Its magnitude is 25 newtons. Therefore, I'll say its x component is plus 25 newtons. And then I'm going to say the mass of desk D is 50 kilograms. So now I can take x components. You see, so if I were going to, I could say that the acceleration in the x direction of object A is 1 over the mass of A times the sum of the x components of forces acting on A. Okay, so that's what we're going to do. We're just going to deal with x components. So then I'm going to say A sub x of the desk is this F push, the x component. This is me on the desk. There's only one force. I won't write all the indices again. divided by the mass of the desk. So that is 25 newtons divided by 50 kilograms, which is plus 0.5 meter per second squared. Okay, so it's a constant force. We're going to get a constant acceleration. So how long does it take? So we're going to say x final minus x initial is 1/2 a sub x t squared. There's zero initial velocity. I guess, we should, starting from rest. So the initial velocity is 0. So I guess we can turn that, x final minus x initial is 25 meters. Okay, so we're given that x final minus x initial is 25 meters. And that is 1/2. Then our acceleration is 0.5 meters per second squared, and then times t squared. Okay, so I guess then we can infer that t squared is 50 meters divided by 0.5 meters per second squared. That seems right, which is 100 seconds squared. So then t is, it's plus or minus 10 seconds, but it's going to be 10 seconds because, okay. So I think I like answer F here. T equals 10 seconds. So wasn't that fun? That was our first force problem. Okay, so we solved our first force problem. We said we know how big the force is and in what direction. We know the mass of the object we're applying the force on, and there's only one force. And that gave us constant acceleration, and we were then able to use the familiar equations from Chapter 3 on constant acceleration. We have here our first example taken directly from the book of a free body diagram. A free body diagram is a kind of visual accounting procedure for adding up the forces acting on a given object. So if you want to know what is going to happen to the ring, is the ring accelerating, or maybe you know it's not accelerating and you want to deduce the consequences of the fact that it's not accelerating, you want to draw a free body diagram for the ring. So you always know what is the object for which you're drawing a free body diagram. You have to be very clear what is the object whose free body diagram you are drawing. In this case, it is the ring. So in this situation, we have a cable which is presumably hanging from the ceiling, and then there is a ring of non-negligible mass hanging from that cable, and there is a person hanging, holding on to that ring, suspending him or herself by that ring. And it looks, if you stare at this, we'll redraw it, that as if the ring seems surprisingly massive. The ring appears to have about half the mass of the person. So we'll talk through that in a minute. So let me redraw this. Okay, so we're going to draw a little kind of circled X, which somehow in Mazur's book denotes the center of mass of the object whose free body diagram we're drawing. And then we want to indicate what is it whose free body diagram we're drawing. So we'll say, okay, this is the ring. Okay? So we are drawing the free body diagram for the ring. And if you make this a little arrow, you want to make sure it's not an arrow that indicates a force. It's like, so I kind of like a dashed arrow or a curved arrow or something. It's just pointing. I usually make it not go all the way to this little circled plus sign, so it's really just there to tell you who is the subject of this free body diagram. And then we want to enumerate all forces acting on the ring. Well, the ring seems to have a significant mass. We'll be able to read this better later as we gain more experience, but there's this arrow pointing downward, and its label says the gravitational force, so G for gravitational force, by Earth on the ring. I guess it's a little r for the ring. I would have made it a big R, but a little r for the ring. And I guess maybe we haven't. So it'll turn out that this equals, here, I'll just write it down anyway. So I think Eric tells you not to write the magnitudes of forces down on diagrams. I often find it convenient to do so. So this is the mass of the ring times little g, okay? So that's how big it is. I know I said here that a scalar equals a vector. Its well, maybe that equal sign means that's what its magnitude is. Okay, then, so what does that mean? Earth's gravity is pulling down on the ring. Why? The ring has a mass, and so there's a gravitational force, which is the ring's mass times little g. Little g is 9.8 meters per second squared, which is the same thing as 9.8 newtons per kilogram. So if you know how many kilograms of mass something has, and you can multiply by little g, and that gets you how many newtons of force Earth applies downward on it when it is near Earth's surface. And then, so we know that there's a gravitational force exerted by Earth downward on the ring, whose magnitude is the mass of the ring times little g. And then we know that there is a contact force exerted by the person on the ring. I guess I don't always draw little arrows over these F's because it's obvious that a force has a direction. It's obvious to me. So anyway, and then I say, well, the arrow kind of shows me the direction. But this will turn out, now we actually don't know why this is true yet. This will turn out to equal the mass of the person times g. I guess I could show you why that's true in a little digression in a second. The basic reason why that's true is that the person is not accelerating and Earth is pulling down on the person. There's only one other force acting on the person, which is the ring is pulling up on the person. So if the ring's pulling up on the person, then the person must be pulling down on the ring. But I'm getting ahead of myself. Then there is this upward force, which is the contact force by the cable on the ring. Okay, so I guess C for cable. I usually make these things saying who's who, all capital. I guess Eric makes them sometimes lowercase. I would have said big C on big R. And then I guess it's always good practice to indicate on your free body diagrams your coordinate system. So we have the x-axis pointing upward. And it's also extremely good practice. If you know the acceleration, then you should say that the acceleration is what it is. This acceleration is 0. It might be that you don't know the acceleration. Then you might want to say the acceleration is a question mark. So this acceleration is 0. So if the acceleration of the ring is 0, and that makes sense because if you sit here looking at the ring, then, well, I guess maybe this isn't necessarily an action shot, but it seems like if the person is just steadily hanging on to the ring and not bouncing up and down, then the ring is not accelerating and the person is not accelerating. So that's a static situation. It's actually the most common situation we'll find when we study architectural structures. So acceleration is 0. So in that case, we'll use the fact that the acceleration is 0 as a constraint on how these arrows' lengths should add up. So we know that the cable is pulling on the ring. The cable is pulling upward on the ring. We know the person is pulling downward on the ring, and we know Earth gravitationally is pulling downward on the ring. And it will turn out that if you take the x component, so if you say the force in the x direction of the cable on the ring plus the force in the x direction, which is the up part of Earth, this is a contact force, I guess this is a gravitational force, Earth on the ring, plus the force in the x direction, which is a contact force of the person on the ring. Maybe I'll I'll do what I more normally do and make it a capital P. Then these three things should add up to 0. The x components of all of these forces should add to 0 because the acceleration of the ring is 0. And that tells you, so of course this has a positive x value, and these two things have negative x values if the x-axis points up. So that tells you that the length of this arrow has to equal the sum of the lengths of these two arrows. Okay, so I'll say that again. The length of this up arrow has to equal the sum of the lengths of these two down arrows. And that's necessary for this acceleration to be 0. So these diagrams, they give you a visual way to just keep track, to enumerate all the pertinent forces. And then they also give you a place to write down information you know about them. And they also, if you have some pretty good idea what their magnitudes, or at least their relative magnitudes should be, then you can indicate that and you can kind of get this immediate visual picture of how things add up. So this plus this length should add up to that length. Oh, that was scary. Good. By the way, I told you I could, as a digression, tell you why this equals the mass of the person times g. So if you were going to draw a free body diagram for the person, so this is a separate free body diagram for the person, then here is the little center of mass cross sign, x sign for the person. And the person, there are only two forces acting on the person. So this is a gravitational force by Earth on the person. And this is a contact force by the ring on the person. And these must be equal in magnitude and opposite in sign because the acceleration of the person is 0 and there are only two forces acting on the person. So if the acceleration of the person is 0 and there are only two forces acting on the person, then those two forces must be of the same magnitude and point in opposite directions so that they balance one another. And you know that the magnitude of the gravitational force by Earth on the person is just the mass of the person times little g. So there are exactly two forces acting on the person, and the person's acceleration is 0. Therefore, those two forces must have the same magnitude and must point in opposite directions so that they can balance one another. They can cancel each other out. So this is the gravitational force by Earth on the person. And you know that the gravitational force by Earth on the person must equal the mass of the person times little g. So therefore, you know that the contact force by the ring on the person must equal the mass of the person times g. And the reason why that has to be true is so that these two forces can balance one another, because the gravitational force downward by Earth on the person must be exactly balanced by the contact force upward by the ring on the person in order for the person's acceleration to be 0. This delicate argument requires that the person is not accelerating. If the person is accelerating, then you have to account for that. Therefore, the contact force by the ring on the person points upward and has magnitude mass of the person times g. Therefore, the contact force by the person on the ring is just the flip side of that same coin. So it points downward and has magnitude mass of the person times g. So in fact, this orange line has the same length as this magenta line, which has the same length as this other magenta line. And I unfortunately did not draw them to scale. If I'd planned ahead, I would have drawn them to scale. So you get that? So by drawing a separate free body diagram for the person, we were able to argue that because the person is not accelerating and because there are only two forces acting on the person, and we know the magnitude of one, we must know the magnitude of the other so they can balance. So therefore, the magnitude of the contact force exerted by the ring on the person must be the mass of the person times g. The mass of the person times g, shorthand for that is the weight of the person. So the contact force, this is basically the definition of the weight of the person. And this equals the weight of the person because the person's not accelerating and there are only two forces acting on the person. So this contact force by the ring on the person has a magnitude, it's upward, and has a magnitude equal to the weight of the person. Therefore, this contact force exerted by the person on the ring, which is just the other side of that interaction pair. I guess maybe we should say an interaction pair is like a coin. And one side is the force of the person on the ring, and the other side of that coin is the force of the ring on the person. So this orange line downward is the same force, it's just the other side of the same interaction pair as the force of the ring on the person. So it's just kind of viewed from a different, it's kind of the opposite side of that interaction pair coin. So this force, the orange arrow pointing down, is the other side of this interaction pair with this contact force of the ring on the person. So it's a kind of a, if you really formally want to know why does this orange arrow, which is the contact force by the person on the ring, have a magnitude of the weight of the person, you have to do this little extra dance here where you say, I'm going to draw a free body diagram for the person. I'm going to argue because the person has zero acceleration, the forces on the person must balance. And I know how big this one is, therefore I know how big this one is. Now, you might say that's like using an awful lot of effort to prove something which is just common sense. Because if you have this ring here, and you stick a person whose weight is, well, let's say it's a 50 kilogram person. So let's say it's about 500 newtons. Okay, so the weight of the person is 500 newtons. So you know, if you have this ring just sitting there, and you stick onto that ring a person whose weight is 500 newtons, you know the downward force of the person on the ring is going to be 500 newtons. You're basically sticking that person's weight onto the ring. But sometimes it's useful to step back and ask, how do you know that? Because if it turns out, suppose it turns out that there's a big, I don't know, maybe this is part of a circus act, and there's a machine that's going to make the cable accelerate upward in some spectacular way. Then suddenly the ring is accelerating and the person is accelerating, and we have to rethink our assumptions. So then you actually do have to go through all this logic more carefully. But so it is kind of important to understand why we can make this statement that this equals the weight of the person, because it will turn out not to be true if everything is accelerating. It'll be bigger than the weight of the person if things are accelerating upward, or it'll be smaller than the weight of the person if things are accelerating downward. I'm kind of introducing some complications. Maybe I shouldn't introduce too many complications. So for now, we're saying this free body diagram is kind of a visual bookkeeping tool that helps us to say, what are all the forces acting on the ring? How big are they, at least approximately? Which direction do they point? And then you can kind of say, what kind of forces are they? And then we can say, how much do they have to balance? If we know that this thing is not accelerating, then we know they all have to balance. Or if we know that the forces don't balance, then we must know that this thing is accelerating. Okay, that's enough on this slide, I think. This is an adaptation and kind of enhancement of a reading question. Think about the familiar example of a basketball dropped from eye level and allowed to bounce a few times. Describe the forces acting on the basketball at its lowest point as it is in contact with the floor and is changing direction from downward to upward motion. So to do that, let's draw a free body diagram of the ball at its lowest point while it is most squished. Include all forces acting on the basketball. Include the direction of each force with its vector arrow. Indicate the relative magnitudes of the forces by the lengths of the arrows. Indicate the direction of the ball's acceleration with an arrow or a dot if it's not accelerating. Oh, when you finish that, draw a second free body diagram for the ball, this time while the ball is in the air. Will the diagram be different while the ball is rising versus falling? Okay, so we're going to see my diagram on the next slide. You might want to think about what your diagram would look like. Maybe I'll try it, and then we'll see what we see in the next slide. So I'm going to draw a diagram for the ball. So I'm going to say, okay, this is the ball, the basketball, and it's at its lowest point. It's when it is most squished. So I think well, first of all, there's one force which is always acting on the ball, which is, this is the gravitational force exerted by Earth on the ball. I like to write, like, what's the letter I'm going to use for the ball? Okay, or the object I'm drawing the free body diagram for. So this thing, by the way, has a magnitude of mass of the ball times little g. What else? I actually think there's only one other force acting on the ball at this time, and it is the contact force exerted by the floor on the ball. Now, which one is bigger? So just a moment ago, the ball was moving downward toward the floor at pretty high speed. And then a moment from now, the ball will be moving upward after unsquishing at pretty high speed. So the ball somehow is in the middle of going from this way to this way. At this instant, while it's most squished, it probably has zero velocity, but its velocity is quickly going from downward to upward. So I think it has a big, actually bigger than g, upward acceleration, probably bigger than g. So I think, yeah, I think it is bigger than g, because you see, if you're accelerating at g, you go from this maximum upward speed to this maximum downward speed in, I don't know, like something on the order of a second or half a second. But when it's at the most squished, I think it's going from this biggest downward velocity to the biggest upward velocity in a much faster time than that, a much smaller time. So I think that we have now a considerably bigger arrow. I'm going to make it as big as I can make it without getting off the end of the board here. This is the contact force of the floor, F for floor, on the ball. And I think it's much bigger than mg, but I don't know exactly how big it is. And so I think the acceleration of the ball is this way. I think it's probably quite a bit bigger than g, but you probably have to watch a slow-mo video to be sure. Okay, so that's what I think we're going to see for that. And then when the ball is just sailing through the air, and it doesn't matter whether it's going upward or downward, I think we're just going to erase this arrow from the floor, because so I'm not touching it anymore. The floor isn't touching it anymore. The only thing that's affecting it in the absence of air resistance is just Earth's gravity. So I think when the ball is in air, whether it is going upward or downward, it's just this one little arrow downward due to Earth's gravity. There's no other arrow. So let's see what I drew. Let's see. Which free body diagram best represents the forces acting on the basketball at the bottom of its motion? So this has only the contact force by the floor on the ball. This has only the gravitational force by Earth on the ball. I don't like either one of those. This one has both of those forces, although they seem kind of similar in magnitude, and that doesn't seem right, because the upward force certainly has to be bigger for the ball to accelerate upward. So I guess the one I like the best is A, alpha. It has the force exerted by the floor on the ball bigger than the force exerted by Earth on the ball. Although I actually think that I should have drawn this upward arrow probably even bigger, because I actually think that the ball's upward acceleration is probably considerably larger than g. But anyway, I think qualitatively I like A, alpha. How about that? So then on the next slide, I think we're supposed to say when the ball is at the top of its motion. So I think the way I would edit my diagram for that is I would simply erase this arrow, because there's no longer any influence of the floor. And also I would change this arrow. So the acceleration is downward, and in fact, its magnitude is g. I know I'm not supposed to make a vector equal a scalar, but anyway, I think it's g downward. Yeah. So I think I like d, delta, for when the ball is at the top of its motion. And in fact, this is the same diagram anytime the ball is not in contact with the floor or with my hands. So then the only force acting on it is gravity if we neglect air resistance. Yeah, and see, this is the same diagram except as a equals 0, but a equals 0 is false. It certainly is accelerating. It's accelerating downward at g. So I like d, delta, for this question. If I were to draw a free body diagram for the basketball when it is halfway back down to the ground, that new diagram would be the same as, slightly different from, very different from the drawing for the basketball when it is at the top of its motion, neglecting air resistance. What do you think? I think it is the same as, A, alpha, it's the same as, because whether it is at the apex or halfway back down, the only force acting on it in the absence of air drag is Earth's gravity. So there's this downward force which is equal to the ball's weight. And it's exerted by Earth on the ball. It's a gravitational force. Consider a car at rest on a road. We can conclude that the downward gravitational pull of Earth on the car and the upward contact force of the road on the car are equal and opposite because the two forces form an interaction pair. The net force on the car is 0, or neither. The two forces are not equal and opposite, or maybe some combination. Well, if the car is at rest on the road, with that rest on the road, then its acceleration is 0. You could even, I might even say like that for its acceleration being 0. So if its acceleration is 0, and we can identify only two forces acting on the car. So there's a gravitational force exerted downward by Earth on the car, and that equals the car's weight. So that's the mass of the car times little g. And then there's this contact force pushing up on the car. So the road is pushing upward on the car. And the car is not accelerating. If there are only two forces acting on the car, and the car is not accelerating, then those two forces must be equal in magnitude and opposite in direction. So the reason why the two forces have to be equal and opposite in this case is because the net force on the car is 0. Actually, Mazur's book, instead of saying the net force, Mazur's book usually says the vector sum of forces. So usually, sometimes you could say the net force, although Mazur says the vector sum of forces. It's really the same thing, but I think Mazur likes you to continue to think that these separate forces they're separate entities whose effect is combined vectorially. The net force makes you think there's just one combination force, and it's maybe, actually there's several interactions and then their influence combined. So this is kind of more correct. But anyway, in either case, it's the same outcome. It's just the vector sum of the forces acting on the car. So I think they are not an interaction pair. You see, I'll tell you why they're not an interaction pair. This is Earth on the car. This is the road on the car. There is a gravitational force of the car on Earth, believe it or not. If Earth is pulling the car downward, then the car actually is pulling the Earth upward, although Earth barely notices because Earth is so massive. And if the road is pushing up on the car, well, then the car must be pushing down on the road. So the upward force by the road on the car and the downward force by the car on the road are an interaction pair, but that second force doesn't appear in our diagram. And the downward force of Earth on the car gravitationally and the upward force of the car on Earth gravitationally are an interaction pair. But again, this is a free body diagram for the car. Only forces acting on the car appear in the car's free body diagram. So for any given interaction pair, you will never see both halves of that interaction pair on the same free body diagram, ever. So, two forces acting on the car. The road's pushing up on the car, that's a contact force. Earth is pulling down on the car, that's a gravitational force. They have the same magnitude in opposite directions. That allows them to sum to 0, which makes sense because the car is not accelerating. And a car seldom accelerates in the vertical direction. I mean, you might be stepping on the accelerator, then there's something else going on which would cause the car to accelerate horizontally. But it's sort of unusual for a car to accelerate in the vertical direction, except maybe if it goes over a bump or if it's going up or down a hill. Okay. Explain briefly in your own words what it means for the interaction between two objects to involve equal and opposite forces. The interaction between two objects. Can you illustrate this with an everyday example? And my everyday example is that was pretty good. I have a not quite everyday example, which comes from the physics classroom, and that is if I pick up the 15-pound medicine ball and I throw it that way, I can feel, as I push the ball forward, I can feel the ball pushing back on me. And in fact, you can see me recoil. If I'm not anchored to the ground, then when I throw the ball, I recoil. So when I push the ball forward, the ball pushes me backward simultaneously. So the force exerted by me on the ball is the same magnitude as the force exerted by the ball on me, except if I'm pushing the ball forward, then the ball is pushing me backward. That's not quite every day, but that's an example. For instance, if I push against some object O that moves, deforms, or collapses in response to my push, is the force exerted by object O on me still equal in magnitude and opposite in direction to the force exerted by me on O? Yes, as a matter of fact. So if I push on something and it squishes, then, see, so here, I'll push on this wall. And so here's a nice sturdy wall, and I push on this wall and it pushes back on me. Fine. Now you might say, oh, now what if the wall collapses? I push on the wall, you see it doesn't push back on me, and that's why it collapses. That is not good reasoning. No, you cannot say that. What happens if the wall collapses is I try pushing on the wall, and then because the wall then deforms, then the force between me and the wall suddenly diminishes significantly in magnitude. So not only is the wall not pushing back on me, I'm not pushing on the wall either. The force between me and the wall suddenly diminishes because I'm not, see, I was like right up against the wall pushing on it. Now the wall kind of stepped back from me when it accelerated away from me, and now we're no longer in direct contact. Or if we are in direct contact, we're not in nearly as close contact. So I think it would be nice to make a more clear model of that. But if you push on something and it collapses, the push exerted by it on you is still the same as the push exerted by you on it. It's just that I think once it starts to collapse, that force diminishes in magnitude. So not only is it not pushing back on you as hard, but you're not pushing on it as hard either. So the two sides of that interaction pair both diminish. It's not just that one of them does. So you have to bear that in mind. So Newton's third law does not stop working when something collapses. It continues. It's just that when something stops pushing back on you, typically the force between you and that thing diminishes. So that's both the force by you on it and the force by it on you. If every force is paired with an equal and opposite force, why is it ever possible for any object to be accelerated? Don't they all just cancel each other out? Well, no, because if I push on the medicine ball with a forward force, the medicine ball pushes on me with a backward force. Those are the same magnitude. But if you want to know what happens to me, you only care about the forces on me. If you want to know what happens to the medicine ball, you only care about the forces on the medicine ball. So that actually is, that's important, and this will come up in the next couple of examples. Have you ever spotted the Tropicana juice train? And you may especially have done so if you are somebody out on the Schuylkill River rowing early in the mornings or out running. The train actually goes right by my house in Yardley, Pennsylvania, and then finds its way down to the Schuylkill River. Or actually, it's usually going the other way. It's going from Florida up north. So, but anyway, it passes by both the campus and where I live. So let's use this Tropicana juice train as a physics example here. We have some vocabulary we need to use, which is that the powered locomotive is what pulls the unpowered cars. Okay, so all these things that say Tropicana on them are cars, and then there's a thing up front that says CSX on it, and it is the locomotive. So here's a puzzle for you about the locomotive. An engine, the locomotive, which is the first vehicle of the train, pulls a series of train cars. Which is the correct analysis of the situation? And, well, you don't really want to watch me draw this, but... Okay, so here is the locomotive, and it's pulling a series of cars. And I think there's a better diagram coming up. Okay, so these are unpowered cars, but the locomotive is pulling the cars. Okay, so the train moves forward because the locomotive pulls forward slightly harder on the cars than the cars pull backward on the locomotive. So maybe the locomotive pulls harder on the cars than the cars pull on the locomotive. You can think about that with what you know about Newton's third law. Well, because action always equals reaction, the locomotive cannot pull the cars. Cars pull backward just as hard as the locomotive pulls forward, so therefore there is no motion, ever. The locomotive gets the cars to move by giving them a tug, during which the force on the cars is momentarily greater than the force exerted by the cars on the locomotive. Oh, so maybe for just an instant we can violate Newton's third law. Force by the locomotive on the cars is momentarily greater than the force exerted by the cars on the locomotive. That sounds... What do we know about Newton's third law? When is it true? I think it's always true. The locomotive's force on the cars is as strong as the force of the cars on the locomotive, but the frictional force by the track on the locomotive is forward and large, while the backward frictional force by the track on the cars is small. Or the locomotive can pull the cars forward only if the locomotive's mass is larger than the mass of the cars. Well, there are an awful lot of cars. Sometimes I've seen a train like a mile long, and there's only one locomotive out front. How could the mass of the locomotive be guaranteed to be bigger than the mass of all of those cars together? So I think answer D, delta, is starting to look pretty good. So it seems like, okay, we have the locomotive pulling on the cars, and we have the cars pulling on the locomotive. And just looking at that one interaction pair is not enough to tell us why the locomotive is able to pull the cars forward. We need to look at the other forces in the problem. For example, there is a frictional force horizontally between the track and the locomotive. And I think you can think about the fact, like, what if the locomotive were in neutral versus what if the locomotive is in drive? You know, if you're kind of used to driving a car, especially a manual transmission car. And so I say the cars are basically all in neutral, whereas the locomotive is in forward gear, and it has a good frictional, and also you could imagine, well, suppose you put grease between the locomotive's wheels and the track. Would the locomotive then be able to pull the rest of the train forward? And I think no, it would not. So let's look at the next page now. So here's my little diagram. So we have a car, and it says Tropicana on it, and it has little wheels, and the car wheels are in neutral. Okay, so it's like if you're driving a manual transmission car, it's like you're in neutral or you're stepping on the clutch. And the thing at the front, the engine, the locomotive, which says CSX on it, it has wheels. It is in gear. So, okay, so it's like in first gear, second gear. And the engine's wheels, the locomotive's wheels, are engaged. So it's as if you don't really care what the friction is between the track and the cars here. The wheels are normally rolling, but you do care a lot about the friction between these wheels and the track. So if you put some grease or some slippery wet leaves underneath these wheels, it wouldn't make any difference. But if you put some grease or some slippery wet leaves underneath the wheels of the locomotive would no longer be able to accelerate the cars. So I think that is the key. So let's see the effect of including or not including the frictional force between the tracks and the wheels of the engine. The way we're going to see that is I'm going to pretend to be the engine in this video clip. Here we go. So let's see what the effect is of including or not including the frictional force of the track on the wheels of the engine. I'm going to be the engine. So here we go. So I'm the engine. Here's the car. And I'm going to pull on the car. And let's suppose for the moment that there's no friction between me and the track. How am I going to arrange that? Well, I'm going to stand on this skateboard thing. We've seen this skateboard thing before. If I stand on this skateboard thing, then I'm standing on rolling wheels. And the cart, well, you know the cart's on rolling wheels, right? We showed you this just a moment ago. The cart is on rolling wheels. What happens if I'm standing on rolling wheels and the cart is on rolling wheels and I pull on the cart? So this is basically like we're both on a sheet of ice. I mean, it's not perfect. The wheels aren't perfect, but we do this. Whoa. Well, actually, in this case, sure enough, nobody seems to move forward. We move toward one another, but our center of mass doesn't accelerate. So that's not very helpful. That apparently is not the whole picture of what causes a train to accelerate forward. So let's get rid of the skateboard. So now I have my car, train car. I am the locomotive, and the locomotive is wearing sneakers, good rubber shoes that have a good frictional contact with the track. So if the locomotive has a good frictional contact with the track, and its transmission is engaged, whereas the cars are all in neutral, unless they're braking, the cars are in neutral. So now I can pull, oh, the casters are behaving kind of funny, but I can pull on the locomotive and I can make it go forward, and then I guess we can go forward together. So I really don't like these casters. I'm going to pull on the car is going to move forward, we're going to move forward together, and this is all possible because there is a frictional force between my shoes and the floor, just as there's a frictional force between the locomotive's wheels and the track. So this works because so you know that a system as a whole will accelerate only if there's an external force acting on that system. So we have a force somehow outside the system. So if the system consists of me, the locomotive, and the car, then the force between me and the car is not an external force, it's an internal force. So that force cannot cause the system as a whole to accelerate. We need some external force. That external force will be the friction between my feet and the floor. So it's the frictional force of the floor acting on my feet. And that is what's causing this system to accelerate forward. And again, we can see what happens when we remove that force. We'll remove that force by putting me on a skateboard. And then, here I am, the locomotive. I'm going to pull on the car. Okay, we can remove toward one another, but our center of mass doesn't accelerate because there's no external force. Let me point out something really important about the system concept and forces, which is that only external forces can accelerate the center of mass of a system. Okay, so we're going to see in a moment that the acceleration of the center of mass of a system is 1 over the total mass of all of the constituents of the system times the vector sum of the external forces acting on the system. So, in other words, the forces that are simply exerted between the internal constituents of a system. Like if I have, so the force between the locomotive and the car does not accelerate the train as a whole. And if you want to accelerate this, if you call the train as a whole the system, that's the locomotive plus the cars, the force exerted between the locomotive and the cars that's an internal force. It's exerted between, it's by one part of the system on another part of the system. That does not accelerate the center of mass of the system. If you want to accelerate the center of mass of the system, you need a force which is external to the system. So in that case, the friction between the track and the locomotive is an external force. So the track, the force exerted by the track on the locomotive in the forward direction due to friction is, in fact, an example of an external force acting on the system. So it can accelerate the train. So that is what accelerates the train. What accelerates the train is the frictional force forward exerted by the track on the train. If the train is speeding up. If the train is slowing down, then there's a backward frictional force by the track on the locomotive. So let's define the system to be the locomotive plus the car. So that's it's our whole little train, a little truncated train. It's a locomotive and one car. Forces internal to the system cannot accelerate the system's center of mass. If you want to change the velocity of the center of mass, you need a force that is external to the system. And by the way, when you look at the two free body diagrams on the next slide, think about where you might see an interaction pair of forces. This is going to be pretty deep. So you're going to see one interaction. You can see an example of an interaction pair in the next slide. I want you to see if you can find it before I point it out to you. Okay, let's look at a free body diagram for the engine up here and a free body diagram for the wagon down here. Now I realize I had a little oops. Somehow there was a vocabulary change. Engine and locomotive are the same thing. It's the thing up front that pulls the train. Wagon and car are the same thing. It's the thing in the back that's towed by the engine or the locomotive. I made a mistake. I changed vocabulary in the middle of the problem. So let's look at these two diagrams. So here I have a free body diagram for the engine, or also known as the locomotive. There are two horizontal forces acting on the engine / locomotive. There is the forward force, which is frictional by the track on the engine. And there is the backward force, which is a contact force by the wagon on the engine, also known as by the car on the locomotive. And notice that this arrow pointing to the right is bigger than this arrow pointing to the left, which is consistent with everything with the engine, the locomotive, accelerating forward. And then let's do a free body diagram for the wagon, also known as the car, So there is a big green arrow to the right here, which is the contact force by the engine on the wagon. And then there's this little purple arrow pointing backward, which is the frictional force by the track on the wagon. And this frictional force by the track on the wagon is small and backwards, and this frictional force by the track on the engine is big and forwards, and that's because the wagons, also known as cars, are in neutral, whereas the engine, also known as the locomotive, is in drive. It's in like first or second gear. But everything is accelerating forward. I mean, the whole train is accelerating forward. Now, do you see an interaction pair here? I think I do. I think this contact force by the engine on the wagon and this contact force by the wagon on the engine form an interaction pair. So the engine is pulling the wagon forward and the wagon is pulling the engine backward, and those are just two sides of the same coin. They're two sides of the same interaction pair of forces. Not only that, but they are both internal forces as far as the engine plus wagon system, the entire train system, is concerned. Internal forces do not accelerate the center of mass of the system. So these two forces are they are complementary parts of an interaction pair of forces. This is a force by the wagon on the engine. This is the force by the engine on the wagon. And notice that if we were to combine the engine and the wagon together into one big system and then draw a free body diagram for that system, the internal forces would not matter. In fact, this is one time when the two parts of this Newton's third law interaction pair would actually legitimately cancel one another, because you're combining the free body diagrams for this object and this object to make a free body diagram that encompasses the system consisting of the two objects together. In that case, you see it's convenient that these two things would cancel each other out, because internal forces make no difference to the free body diagram for the system as a whole. So then you would just have this yellow arrow to the right and this much smaller purple arrow to the left. This is friction because the track, the engine is in like first gear, second gear, and this is backward friction just because the wheels have a tiny bit of friction even though they're in neutral. That's if you were going to make a free body diagram for the system as a whole. So again, if you were going to make a free body diagram for the train system as a whole, then it would look something like this. It would still have this acceleration pointing forward, that same forward acceleration, and it would have this yellow arrow pointing, it's not a very good yellow. It would have this yellow arrow pointing forward, which is the frictional force. I usually just say F for friction, but frictional force, which is the track on the engine. And then there would be this little purple backward force, which is, it's also a frictional force, which is the track on the wagon, also known as a car. So those are the only two external forces. And you can see this one is much bigger than this one, so it's consistent with the acceleration of the train as a whole being forward. And maybe I would make this a dashed line so you're sure that you don't think this is a force. It's just telling you what we're drawing the free body diagram for. Okay, so I think that was kind of informative. It went on for a little while, but I think, so you see, the reason why the locomotive is able to pull the rest of the train forward is because the frictional force exerted by the track on the locomotive is large and positive, whereas the frictional force exerted by the track on each car or wagon is small and backward. Isn't that cool? So as a matter of fact, this frictional force exerted by the track on the engine, which is forward, has to be bigger than the sum of all of the tiny little backward frictional forces by the track on the individual cars or wagons. So this, which I've redrawn here, is a really useful relationship. The acceleration of the center of mass of a system equals the vector sum of the external forces acting on that system divided by the total mass of the system. So you only need to add up the external forces acting on the system. So for instance, when we wanted to draw the free body diagram for the train as a whole, then we only had to consider the external forces, the forces that involve something outside of the train, pushing or pulling on something inside of the train. So the force between the car and the locomotive, or between the wagon and the engine, is irrelevant to the acceleration of the center of mass of the system. If you're drawing a free body diagram for the system as a whole, you only care about the external forces. In this case, this would be like this small backward frictional force of the track on each wagon or car, and the large forward frictional force of the track on the engine, also known as the locomotive. So this is actually useful because even if the several pieces of a system are behaving in a complicated way, you can find the acceleration of the center of mass of the system by considering only external forces that act on the system. So once again, a careful choice of system boundary often makes the analysis much easier. We're going to see more examples of this soon. By the way, there are a couple places where this topic arises in some worksheets, so we'll try to practice it here first. But by the way, I think somewhere coming up I have there's a little video clip of somebody dropping a slinky from a tall building. And the behavior of the constituents of the slinky is kind of complicated. But it turns out that the center of mass of the slinky, when you drop it, still just drops with a downward acceleration of g, because there's only one once you let go of the slinky, there's only one external force acting on the slinky, and that is the external force of gravity, which that force then equals the weight of the slinky, and then you divide by the mass, you just get g. So the center of mass of the slinky still accelerates downward at g, even though when you see the video clip, the internal constituents of the slinky are behaving in a complicated way. I'll see if I can find that video clip for you.
It happens really fast.
All right.
3, 2, 1, drop.
Okay, that's all for now. We will continue next time with the rest of Chapter 8. So I will let the semester schedule for video assignments slip by one day, and we'll continue next time and finish up Chapter 8, and then we can make up that squeezed out day later when the video assignments spread out a little bit. So I'll see you in class for Worksheet 8.